For 90 years, the most abundant form of matter in the universe has remained completely invisible to us. Not because our instruments are too weak, not because we haven't been looking hard enough, but because this substance simply refuses to interact with light in any way. It doesn't emit light. It doesn't reflect light. It doesn't even absorb light to cast a shadow. And yet, without it, galaxies would tear themselves apart, stars would never have formed, and the cosmos as we know it wouldn't exist at all. Wait before you continue. If you're enjoying this, just hit subscribe. It literally takes 1 second, and you'll keep getting videos like this. Don't watch and disappear. Be part of the people who actually grow with this. In November of 2025, a paper published out of the University of Tokyo sent a quiet but powerful shockwave through the astrophysics community. A researcher named Dr. Tomonori Totani had been sifting through 15 years of archived telescope data, and what he found buried in the noise of the Milky Way's gamma-ray background was something no one had ever cleanly identified before. A pattern, a shape, a signal with a very specific energy fingerprint coming from a region of space precisely where dark matter is predicted to live. This might be the first time in human history that we have seen dark matter leave a mark. To understand why this is significant, we have to go back to where the story began. And it begins with a peculiar, outspoken, and genuinely brilliant Swiss astronomer who had a habit of calling his colleagues names, and an even stronger habit of being right. Fritz Zwicky was born in 1898 and spent the bulk of his career at the California Institute of Technology. He was, by many accounts, difficult to work with. He feuded with colleagues, invented insults for scientists he considered mediocre, and generally operated outside the polite conventions of academia. But his scientific instincts were extraordinary. He coined the term supernova to describe the catastrophic explosions of dying stars. He catalogued tens of thousands of galaxies across the sky. He published hundreds of papers across a dazzling range of astronomical topics. And in 1933, at age 35, he stumbled onto something that would haunt physics for the rest of the century and well into the next. Zwicky was using the Mount Wilson telescope, the same instrument Edwin Hubble had used just a few years earlier, to prove that the universe was expanding to measure the redshift of galaxies in the Coma cluster. Redshift is the stretching of light as a source moves away from an observer. The more stretched the light, the faster the source is receding. By measuring this stretching across multiple galaxies in the same cluster, Zwicky could calculate how fast each one was moving. What he found made no sense. The galaxies in the Coma cluster were moving at speeds of more than 2,000 kilometers per second relative to one another. At those velocities, the cluster should have been destroyed long ago. The galaxies should have simply flown apart from each other like sparks from a fire. There was nothing physically coherent holding them together, not if you only counted the mass of the visible stars and gas. Zwicky did the math. He calculated the total mass needed to gravitationally hold the cluster together at those observed speeds. The visible matter, every star, every cloud of gas that his telescope could detect, accounted for only about 1/10 of the required mass. The cluster needed 10 times more mass than could be seen. Something massive and invisible had to be present, generating enough gravitational force to keep the system from flying apart. He called it dunkel materie, dark matter. At the time, most physicists assumed Zwicky had made a measurement error, or that his analysis was flawed in some way. His abrasive personality didn't help his case. But over the following decades, the evidence kept accumulating from completely independent directions, and one by one, the skeptics were forced to take the idea seriously. In the 1970s, an astronomer named Vera Rubin made her own landmark contribution. Rubin was studying the rotation curves of individual galaxies, essentially. She was measuring how fast stars at different distances from the galactic center were orbiting around it. According to standard gravitational physics, stars farther from the center of a galaxy should orbit more slowly, just as the outer planets of our solar system move more slowly around the Sun than the inner ones do. This is simply how gravity works over distance. But Rubin found that stars at the outer edges of galaxies were orbiting just as fast as stars much closer to the center. The rotation curves were flat when they should have been declining. And the only way to explain flat rotation curves was to assume that a massive, invisible component was embedded throughout the galaxy, extending far beyond the visible disk of stars and adding gravitational pull at every radius. Rubin found this same pattern in more than 60 galaxies. It was not a fluke, it was a law. This was the observation that forced mainstream science to take dark matter seriously as a real physical component of the universe, not just a measurement artifact. Dark matter wasn't just hiding in galaxy clusters. It was wrapped around every single galaxy in a vast, invisible sphere that physicists began calling the halo. Today we understand that dark matter accounts for roughly 84% of all matter in the universe. The ordinary matter, everything made of protons, neutrons, and electrons, every atom that forms every star, planet, human, and grain of dust, makes up only about 16%. For every kilogram of normal matter in the universe, there are roughly 5 kilograms of dark matter. It is the dominant form of matter by an enormous margin, and we still do not know what it actually is. That is the situation as of the mid-2010s. Physicists had built an overwhelming case for dark matter's existence based on gravitational evidence alone. But gravity tells you something is there. It doesn't tell you what that something is made of. To answer the identity question, you need to detect dark matter particles directly or infer their presence through their interactions with other particles. Two families of candidates have dominated the theoretical landscape. The first are called weakly interacting massive particles, or WIMPs. The second are called axions. Both remain theoretical at the moment, neither has been definitively detected in a laboratory setting. But WIMPs have a particular property that makes them interesting for observational astronomy, and it's this property that brings us to Dr. Tatani's discovery. WIMPs are predicted to arise from an extension of the standard model of particle physics called supersymmetry. The standard model is the most rigorously tested framework in all of science. It describes the behavior of all known fundamental particles and the forces between them with extraordinary accuracy. Supersymmetry proposes that every particle in the standard model has a corresponding partner particle, differing in certain quantum properties. The lightest of these supersymmetric particles, in many theoretical frameworks, would be stable, massive, and weakly interacting. It would be, in short, a WIMP. WIMPs are predicted to have masses somewhere between 10 times and several thousand times the mass of a proton. Yes, that range is uncomfortably wide, but it reflects genuine theoretical uncertainty about the details of supersymmetry rather than a failure of the concept itself. WIMPs interact gravitationally, which is why they can form halos around galaxies and hold galaxy clusters together. Beyond gravity, they interact only via what physicists call the weak nuclear force, one of the 4 fundamental forces of nature. This weak interaction means they almost never collide with or affect normal matter, which is why they're so hard to detect. But here is the critical property. WIMPs are their own antiparticle. In the standard model, every particle has a distinct antiparticle counterpart. The proton has the antiproton, the electron has the positron. When a particle meets its antiparticle, they annihilate each other, converting their combined mass into energy in the form of radiation, typically photons. This is the most direct expression of Einstein's famous equation relating energy and mass, and it is a spectacularly efficient process. Every gram of matter that annihilates with every gram of antimatter releases an amount of energy equivalent to an atomic bomb many times over. WIMPs, being their own antiparticle, would annihilate whenever 2 of them collide. The energy released would take the form of gamma rays, extremely high-energy photons at the upper end of the electromagnetic spectrum. The energy of these gamma rays would be directly related to the mass of the WIMPs that produced them, giving the annihilation signal a specific and identifiable energy fingerprint. This is what makes WIMP annihilation detectable in principle. If dark matter halos around galaxies are dense enough, WIMPs should be colliding and annihilating constantly, producing a diffuse glow of gamma rays spread across the structure of the halo. That glow would be invisible to the naked eye, but detectable by a gamma-ray telescope, a spacecraft specifically designed to detect and map high-energy photons arriving from space. The Fermi Gamma-Ray Space Telescope, launched in 2008, is exactly this kind of instrument. Over the 15 years since its launch, Fermi has been continuously scanning the sky, detecting and recording the arrival of gamma rays from across the cosmos. It has built up an enormous catalogue of gamma-ray observations covering every direction in the sky, at every energy level within its detection range. The challenge is that gamma rays come from many sources. Pulsars, rapidly spinning neutron stars, emit intense gamma-ray beams. Supernova remnants produce them. The violent jets of active galactic nuclei pour them out in enormous quantities. The hot, compressed matter spiraling into black holes radiates them. The center of our own galaxy is a blinding storm of gamma-ray activity from dozens of overlapping sources. Picking out the faint, diffuse signal of WIMP annihilation from this cacophony of astrophysical noise is an extraordinarily difficult signal processing problem. Dr. Totani approached this problem methodically. He began in early 2024 by pulling 15 years of Fermi data, specifically focusing on regions of the sky away from the galactic center where the background noise is most intense. Working source by source, he built up a detailed model of the known contributors to the gamma-ray background and subtracted them out. This is a painstaking process. Every known pulsar, every catalogued supernova remnant, every mapped region of gas and dust had to be accounted for. What remained after this careful subtraction was unexpected. There was a residual gamma-ray signal distributed across the sky in a shape that closely matched the predicted three-dimensional structure of the Milky Way's dark matter halo, not concentrated in the galactic plane where visible matter lives, but spread out in a roughly spherical arrangement, extending far above and below the plane of the galaxy, exactly as halo models predict. And the energy of the signal was centered at approximately 20 giga-electron volts. 1 giga-electron volt is a unit of energy. The electron volt is defined as the energy gained by a single electron when it moves through an electric potential difference of 1 volt. A giga-electron volt is 1 billion electron volts. This might sound abstract, but in particle physics terms, 20 giga-electron volts corresponds to a particle mass of about 20 times the proton mass. This falls comfortably within the predicted mass range for WIMPs. For the first time, the morphology, the shape of a gamma-ray signal, matched the dark matter halo, and the energy, the spectrum of the signal, matched what WIMP annihilation should produce. These two independent pieces of evidence, pointing in the same direction, is precisely what makes Totani's paper so significant to the physics community. To appreciate the scale of what this would mean, consider what dark matter actually does in the universe's history. In the earliest moments after the Big Bang, the universe was a nearly uniform soup of particles at unimaginable temperatures. Ordinary matter and radiation were tightly coupled. Light was trapped, unable to travel freely, and the universe was opaque. Dark matter, however, was already free to move and respond to gravity because it doesn't interact with light. While ordinary matter was stuck in a hot plasma, dark matter began to clump. Slight overdensities, regions marginally denser than their surroundings, began to attract more dark matter through gravity, growing denser still. These dark matter overdensities became the seeds of cosmic structure. When the universe cooled enough for ordinary matter to separate from radiation, an event that occurred roughly 380,000 years after the Big Bang, leaving behind the thermal imprint we now call the cosmic microwave background, ordinary matter was free to fall into the gravitational wells that dark matter had already prepared. Dark matter halos became the scaffolding around which galaxies assembled. Gas fell in, cooled, and collapsed into the first stars. Stars clustered into galaxies. Galaxies grouped into clusters. The entire large-scale structure of the cosmos, the web of filaments, sheets, and voids that characterize the universe on the largest scales, grew out of those initial dark matter overdensities. Without dark matter to provide the early gravitational architecture, the universe would not have evolved the structure needed for galaxies, stars, or planets to exist at all. Dark matter is not peripheral to our existence. It is foundational to it. So identifying what dark matter actually is ranks among the most consequential open questions in all of science. Professor Carlos Frenk, one of the architects of the cold dark matter theoretical framework and a lifetime researcher in this field, has compared the significance of identifying dark matter to the importance of Charles Darwin's theory of evolution by natural selection. That is not a casual comparison. Darwin's theory reorganized our entire understanding of life on Earth. It provided a mechanism that connected and explained vast bodies of previously disparate observation. Identifying dark matter would do something comparable for physics. It would connect the quantum world of particle physics to the gravitational world of cosmology in a way that our current theories cannot fully accomplish. It is not the kind of claim you make lightly, which is why the scientific community is being careful. Totani's result is exciting, genuinely, historically exciting, in a way that dark matter research hasn't been in years. But there are open questions that need to be resolved before this can be called a confirmed detection. The first concerns the density of WIMPs implied by the signal. The strength of the gamma-ray emission Totani measured would require a significant concentration of WIMPs within the Milky Way's halo. But our best models of how WIMPs should be distributed derive from the cosmic microwave background data and from N-body simulations of cosmic structure formation suggest the concentration may be higher than expected. This doesn't rule out the WIMP interpretation, but it means the theoretical models need to be revisited and refined. The second issue involves the exact energy spectrum of the signal. Because the mass of WIMPs is still theoretically uncertain, ranging across those orders of magnitude, from roughly 10 to several thousand proton masses, the predicted annihilation energy spectrum covers a correspondingly wide range. Pinning down the precise spectral shape of the observed signal and matching it to a specific WIMP mass will require more data and more careful analysis. Third, and perhaps most importantly, scientific confidence in a dark matter detection would be enormously strengthened if the same signal appeared elsewhere. The standard prediction of dark matter models is that wherever large concentrations of dark matter exist, WIMP annihilation should occur, and gamma rays should be produced. The Milky Way's neighbouring dwarf galaxies are excellent candidates for follow-up searches. These small, dense satellite galaxies are believed to be among the most dark matter-dominated objects in the universe. Their stars move so fast relative to their total visible mass that dark matter must constitute an overwhelming fraction of their total mass. A corresponding gamma-ray signal from these dwarf galaxies would be powerful corroborating evidence for the WIMP interpretation of Totani's result. This is exactly where the next generation of observational tools comes in. The Vera Rubin Observatory in Chile represents one of the most ambitious astronomical projects in recent history. Vera Rubin herself was one of the most important figures in establishing dark matter as a serious scientific subject. Her systematic study of galaxy rotation curves in the 1970s, covering more than 60 galaxies, provided the most comprehensive and convincing evidence up to that point that dark matter was real, pervasive, and essential. She spent decades battling against the skepticism of colleagues who were reluctant to accept a substance that left no observable imprint beyond gravity. She persisted, refined her measurements, and eventually forced the scientific community to accept the evidence. The observatory named in her honor reflects the magnitude of her contribution. The Vera Rubin Observatory came online in June of 2025. It is equipped with an 8.4-meter mirror and the world's largest digital camera, a 3.2 billion pixel instrument capable of imaging an area of sky 35 times the area of the full moon in a single exposure. Each night, it takes hundreds of wide-field images of the southern hemisphere sky, generating roughly 20 terabytes of data, the equivalent of approximately 78 standard smartphones' maximum storage capacity every single observing night. Over its planned 10-year survey, the Rubin Observatory is expected to accumulate more than 60 petabytes of raw image data. A petabyte is 1 million gigabytes. 60 petabytes is 60 million gigabytes, a dataset of a scale that requires purpose-built computing infrastructure just to store and process. The scientific goals of the Rubin survey are broad. It will map billions of individual stars and galaxies with unprecedented positional accuracy and temporal coverage, meaning it will catch objects that change over time, from supernovae to asteroids to variable stars. But for dark matter research, the Rubin Observatory offers something specifically powerful. By tracking the gravitational lensing of billions of background galaxies is the bending of their light by foreground mass concentrations. It will map the distribution of dark matter throughout the universe with a precision that has never been achieved before. This will allow physicists to test whether the halo shapes and densities predicted by WIMP models match what is actually observed across a vast sample of galaxies and galaxy clusters. Complementing this observational program are underground laboratories and particle accelerators, continuing their direct searches for dark matter particles. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, has been specifically searching for evidence of supersymmetric particles that would support the WIMP hypothesis. While no definitive WIMP signal has emerged from those searches, the experiments have progressively constrained the properties that WIMPs could have, narrowing the theoretical parameter space in ways that inform both direct detection experiments and indirect searches like Titani's. Underground laboratories, meanwhile, are searching for the direct scattering of dark matter particles off atomic nuclei. The idea is simple in principle. If WIMPs are passing through the Earth in enormous numbers, as the dark matter halo models suggest they should be, then very occasionally one should collide with an atomic nucleus in a dense target material. The recoil of that nucleus would release a tiny amount of energy, detectable as a faint flash of light or a small electrical pulse in a sensitive detector. Experiments like Lux Zeppelin in the Homestake mine in South Dakota and Panda X in the China Jinping underground laboratory are running precisely this kind of search, using multi-ton liquid xenon detectors shielded from cosmic rays by hundreds of meters of rock overhead. These underground searches and Titani's indirect detection approach are complementary. A direct detection event in an underground laboratory and a gamma-ray signal in the Fermi data pointing to the same WIMP mass would constitute overwhelmingly powerful evidence for dark matter's identity. The two approaches triangulate on the answer from completely different directions. There is a reason scientists have been cautious despite Titani's compelling result. The history of dark matter research is littered with signals that initially appeared promising before being reinterpreted as known astrophysical processes. In 2014, a different group of researchers announced a gamma-ray excess near the galactic center with properties consistent with WIMP annihilation. That excess is still debated. Subsequent analysis has provided alternative explanations, involving a population of unresolved millisecond pulsars, and the scientific community has not reached consensus on whether the galactic center excess represents dark matter or conventional astrophysics. Tatani's signal, emanating from the full extent of the dark matter halo rather than just the galactic center, is structurally different from that earlier claim, which is one reason it has been received with particular interest. But the lesson of the galactic center excess is that apparent dark matter signals can have unexpected explanations, and vigilance is warranted. The search for dark matter has been, in one sense, a story of repeated frustration. Since Zwicky's original observation 90 years ago, every subsequent effort to directly identify what dark matter is made of has come up empty. The WIMP hypothesis, while theoretically elegant, has survived several decades of increasingly sensitive, experimental searches without a confirmed detection. Some physicists have begun to take seriously the possibility that WIMPs do not exist in the form the simplest supersymmetric models predict, and that dark matter might be something more exotic, a new category of particle interacting through forces we haven't yet characterized, or a modification of gravity that produces dark matter's gravitational effects without requiring new particles at all. But Tatani's result is a reminder that the search is not exhausted. 15 years of Fermi data, analysed with a careful and systematic approach, have produced something genuinely new. The signal may have an explanation that doesn't involve dark matter, but it may not. And the fact that it matches two independent predictions of the WIMP model, the spatial morphology of the halo and the energy scale of the annihilation signal, makes it harder to dismiss. The physics of WIMP annihilation is well understood in its basic outlines. When two WIMPs collide and annihilate, the products depend on the mass of the WIMPs and the specific coupling channels predicted by the supersymmetric model in question. In many scenarios, a significant fraction of the annihilation energy goes into producing pairs of bottom quarks and their antiquark counterparts. These quarks quickly bind into composite particles called B mesons, which are unstable and decay through a cascade of intermediate particles, eventually producing a continuum of gamma rays with a characteristic energy spectrum. This spectrum rises steeply from low energies, peaks at a characteristic energy related to the WIMP mass, and falls off above that peak. The peak at 20 giga-electron-volts in Tatani's data corresponds to a WIMP mass of roughly 40 to 80 giga-electron-volts, well within the range that theoretical models predict and that direct detection experiments have not yet been able to rule out. There is something philosophically striking about how this search has unfolded. Dark matter was inferred from the motion of galaxies, from the behavior of visible objects that have nothing obviously to do with particle physics. And yet the answer, if WIMPs are correct, lies in the deepest subatomic structure of matter, in a layer of reality that particle physicists access through machines that smash protons together at nearly the speed of light. The two most different scales of physical inquiry, the cosmological and the subatomic, are linked by the same substance, and understanding that substance requires both cosmology and particle physics to speak to each other in ways they are only beginning to learn. This is perhaps the deepest reason why dark matter research matters beyond the immediate scientific question. Physics in the 20th century produced two towering theoretical frameworks, quantum mechanics and general relativity, that together describe the universe at the smallest and largest scales with extraordinary precision. But these two frameworks are fundamentally incompatible with each other. They cannot both be correct as final descriptions of reality. Dark matter sits precisely at the interface between them. A dark matter particle is a quantum mechanical entity described by the mathematics of field theory and particle physics. But its observable effects are gravitational, described by Einstein's general relativity. Understanding dark matter may not by itself resolve the incompatibility between quantum mechanics and general relativity, but it will certainly advance our understanding of how those two realms connect. Professor Frank's comparison to Darwin is worth dwelling on for a moment. Before Darwin, the extraordinary diversity of life on Earth was a profound mystery. Thousands of species existed, clearly related to one another in complex ways, clearly adapted to their environments, but with no coherent mechanism to explain how this had come about. Darwin's theory, natural selection, acting on heritable variation, provided that mechanism. It did not just explain one observation. It organized the entire field of biology around a single coherent principle that connected fossils to anatomy, to behavior, to ecology. The theory of evolution didn't just answer a question. It transformed the conceptual foundation of an entire science. Something analogous could happen if dark matter is identified. Right now, the standard model of particle physics is an extraordinarily successful but obviously incomplete description of fundamental reality. It describes all known particles and forces with stunning precision, but it has no dark matter candidate within its framework. Identifying dark matter would require extending the standard model, adding new particles and possibly new forces to the theoretical description of nature. That extension would reorganize our understanding of particle physics around a new conceptual foundation, just as Darwin reorganized biology. The implications would ripple through physics for generations. What scientists know right now is this: the signal totally identified in Fermi data has the right shape, emerging from the predicted morphology of the Milky Way's dark matter halo. It has the right energy, centered at a scale consistent with WIMP masses in the theoretically favored range. And it appears in a region of the sky where the competing background sources of gamma rays are relatively well understood and have been carefully subtracted. These are not trivial agreements. What scientists still need to establish is whether the WIMP density implied by the signal's brightness is consistent with our models of how dark matter is distributed, whether the precise energy spectrum can be matched to a specific WIMP mass with more detailed analysis, and whether the same signal appears in the dark matter halos of nearby dwarf galaxies, where it should appear if WIMPs are responsible. The Vera Rubin Observatory's first data releases in 2026 will contribute. Future gamma-ray telescopes, including proposals for next-generation instruments with greater sensitivity than Fermi, will contribute. The continued operation of underground direct detection experiments will contribute, and particle accelerators will continue to search for supersymmetric particles in high-energy proton collisions. This is what science looks like when it is closing in on a major discovery, not a single definitive experiment, but a convergence of evidence from multiple independent directions, each approach illuminating a different facet of the same underlying truth. The 90-year-old question that Fritz Zwicky first raised while staring at the anomalous motion of galaxies in the Coma cluster may finally be approaching an answer, not because a single breakthrough has solved it, but because decades of accumulated theoretical development, instrument building, and painstaking data analysis have positioned the field at a threshold. Dark matter shaped the universe before the first star ever ignited. It provided the gravitational scaffolding that allowed hydrogen to collapse into the earliest suns. It held together the first galaxies as they assembled from the cooling aftermath of the Big Bang. It has been woven into the structure of the cosmos for the entire 13.8 billion year history of the universe. And it is here, woven into the halo of our own galaxy, right now passing through you, and through this room, and through the earth beneath you, without leaving any trace you could feel or see. The fact that something so dominant and so fundamental has resisted our best attempts at identification for so long is itself a remarkable testament to the strangeness of the universe we inhabit. We built civilization, we invented science, we mapped the cosmos from the quantum scale to the observable universe. And yet, the majority of matter in existence has remained a complete mystery. That might be changing. Dr. Tatani's signal is not a final answer. It is a clue, perhaps the most compelling clue the field has produced in decades. Whether it leads to a confirmed detection of WIMPs or to a deeper mystery is something only continued research will determine. But the quality of the evidence, the care of the analysis, and the convergence with theoretical predictions give physicists genuine reason to believe they are looking at the right place and the right energy scale at last. The nature of dark matter is one of the greatest unresolved questions in the history of science. The answer, when it comes, will change the way we understand what the universe is made of, how it came to be the way it is, and where the boundaries of our current physical theories truly lie. If you find this kind of research as compelling as the scientists working on it do, and the depth of human curiosity and effort behind these discoveries, consider supporting the kind of content that takes the time to explain it carefully. Liking and subscribing helps these explanations reach more people who are asking the same questions. The investigation continues. In underground laboratories, shielded from the surface by hundreds of meters of rock, in the control rooms of particle accelerators in Switzerland, in the data pipelines of the Vera Rubin Observatory, which has just begun its 10-year survey of the southern sky, and in the archives of the Fermi Telescope, where 15 years of gamma-ray observations are still being sifted through for signals that earlier analyses might have missed. We are living in a moment when a 90-year-old mystery may finally be yielding. The universe has kept this secret for a very long time, but the evidence is accumulating, the tools are improving, and the signal, if it holds, is speaking in a language that physicists are beginning to understand. To fully appreciate the difficulty of what Tatani accomplished, it helps to understand the environment in which he was searching. The Milky Way's galactic center is one of the most electromagnetically hostile regions of the sky. Within a few hundred light-years of Sagittarius A star, the 4 million solar mass black hole at the heart of our galaxy, the density of stars, gas clouds, and energetic phenomena is staggering. There are ancient supernova remnants still expanding from explosions that occurred thousands of years ago. There are pulsars spinning hundreds of times per second, each one a lighthouse of gamma radiation sweeping through the galaxy. There are enormous bubbles of hot plasma called the Fermi bubbles, extending 25,000 light-years above and below the galactic plane, first discovered in Fermi data in 2010 and still not fully understood. And there are the jets and outflows from Sagittarius A star itself, contributing to a gamma-ray background so bright that it has long been the primary challenge for any dark matter search in the galactic center region. By deliberately avoiding the galactic center and focusing on the wider halo region, Tatani was making a strategic choice. The halo is less bright in gamma rays, meaning the dark matter signal, if present, would be weaker in absolute terms. But it would also be far easier to characterize the background because the astrophysical sources in the halo are fewer, better understood, and more individually resolvable. Trading signal strength for background clarity was a reasonable strategy, and it appears to have paid off. The shape of the dark matter halo itself deserves more attention because it is one of the things Tatani used to validate his result. Dark matter halos are not perfect spheres. They are described by density profiles that fall off with distance from the center, according to specific mathematical functions. The most commonly used profile is called the Navarro-Frenk-White profile, named after the 3 researchers who derived it from N-body simulations of structure formation in the 1990s. This profile predicts that the density of dark matter rises steeply toward the center of the halo and falls off gradually toward the outer edges. If you integrate the expected WIMP annihilation rate, which goes as the square of the local density, because you need 2 WIMPs to meet over this density profile and project it onto the sky, you get a predicted map of where the gamma-ray emission should be brightest and how it should fade with angular distance from the galactic center. Tatani compared the observed residual gamma-ray emission to this predicted map and found a compelling match. The emission peaked where the halo models predicted it would peak. It faded at the rate the models predicted it would fade, and it showed the expected spherical symmetry rather than the flattened distribution that would be expected from gamma-ray sources concentrated in the galactic disk. This morphological matching is scientifically critical because it is completely independent of the spectral analysis. The shape of the signal tells you where the emission is coming from. It encodes spatial information about the source structure. The spectrum of the signal tells you what the emitting process is. It encodes information about particle energies and masses. When both independent lines of evidence point to the same conclusion, dark matter, halo structure, and WIMP annihilation energy, the combined case is far stronger than either piece of evidence alone. There is a third element worth discussing. The galactic center gamma-ray excess, mentioned earlier, first reported around 2009 and extensively analyzed in subsequent years, showed evidence of excess gamma rays at a few giga-electron volts above the known background, clustered toward the center of the galaxy. This excess has been one of the most debated signals in astroparticle physics. Initial analyses suggested it was consistent with annihilation of WIMPs with masses of around 30 to 50 giga-electron volts through channels involving bottom quarks. Later analyses proposed that the excess could be explained by an unresolved population of millisecond pulsars, rapidly spinning neutron stars that emit gamma rays and are known to be prevalent in the old stellar populations, concentrated toward the galactic center. The debate over the galactic center excess has continued for well over a decade without resolution, but Tatani's halo signal is structurally distinct from that galactic center excess in an important way. Millisecond pulsars being embedded in the stellar population would be concentrated in the galactic disk and bulge. They would not produce emission extending into the high-latitude halo region in the spherical distribution Tatani observes. If his signal were caused by an unresolved pulsar population, it would look different spatially. The fact that it closely follows the predicted dark matter halo profile rather than the stellar distribution is a meaningful discriminant. This does not completely rule out conventional astrophysics explanations. The history of the field teaches humility on that score. But it does mean that the simplest alternatives don't immediately explain the data. That is an important distinction. The history of searches for dark matter particles also reveals something interesting about scientific expectations and how they have evolved. When WIMPs first emerged as a theoretical candidate in the 1980s and 90s, physicists had a strong intuition that they would be discovered relatively quickly. The basic framework of supersymmetry was well developed. The predicted mass range was accessible to experiments being planned at the time, and there was optimism that the Large Hadron Collider, whose construction began in the 1990s and which started taking data in 2008, would produce supersymmetric particles directly. That optimism turned out to be premature. The Large Hadron Collider's first major run, culminating in the discovery of the Higgs boson in 2012, found no evidence for the supersymmetric particles that would have been the most natural WIMP candidates. Subsequent runs at even higher energies have continued to find nothing beyond the standard model in the mass ranges most theorists considered most likely. Underground direct detection experiments grew from kilogram-scale detectors to multi-ton experiments, improving their sensitivity by many orders of magnitude, and still found no confirmed WIMP scattering signal. This long series of null results led some physicists to propose that the simplest WIMP models were ruled out, and that dark matter must be something else entirely. The proposed alternatives range from Axion's extremely light particles originally proposed to solve a different problem in quantum chromodynamics, the theory of the strong nuclear force to sterile neutrinos, to primordial black holes, to more exotic constructs like self-interacting dark matter or fuzzy dark matter involving ultralight particles with wave properties on astrophysical scales. Each of these alternatives has its own observational signatures and its own dedicated experimental search program. Axion searches use sensitive resonant cavity detectors called haloscopes that look for the conversion of dark matter axions into microwave photons in strong magnetic fields. Sterile neutrino searches look for X-ray signals from dark matter decay. Primordial black hole searches use gravitational lensing surveys and observations of gravitational wave merger events. The point is that the dark matter problem has generated a remarkably rich and diverse experimental program across an enormous range of physics disciplines. Astronomers, particle physicists, cosmologists, nuclear physicists, and gravitational wave researchers all have a stake in the outcome. The eventual answer, whatever it turns out to be, will connect threads across all of these fields. It is worth pausing to consider how remarkable it is that we are even able to have this conversation. The fact that we know dark matter exists, that we can confidently assert that the majority of matter in the universe is invisible, has been present since the Big Bang, and has shaped every structure in the cosmos, is the result of generations of patient scientific work. Zwicky's original observation in 1933 was disregarded for decades. Vera Rubin's rotation curve measurements in the 70s were initially met with skepticism. The cosmic microwave background observations in the 1990s that encoded the early universe's dark matter content were analysed by teams working at the edge of what computing technology could handle at the time. The Fermi Telescope that is now providing Totani's gamma-ray data represents 15 years of accumulated observations, calibrated against a background model built from thousands of individually catalogued sources. Each of these steps was necessary. None of them was sufficient alone. Science accumulates in this way, not through sudden revelations, but through the slow accretion of evidence, technique, and understanding, until the weight of knowledge tips a balance that has been building for years. The 20 giga-electron-volt signal in the Fermi data may be that tipping point, or it may be another step along a longer path. Either way, it represents the state of the art in humanity's effort to answer a question that has been open for 90 years. There are additional theoretical considerations that bear on the interpretation of Totani's signal. One concerns the predicted self-annihilation cross-section of WIMPs, a quantity that describes how likely two WIMPs are to annihilate when they encounter each other. This cross-section is not a free parameter. It is related through particle physics arguments to the abundance of WIMPs in the universe today. The argument works roughly as follows. In the early universe, WIMPs were produced in large numbers when the temperature was high enough for them to be created in particle collisions. As the universe expanded and cooled, WIMP production shut off. At some point, the universe became too sparse for WIMPs to find each other frequently enough to annihilate as fast as they were being diluted by expansion, and their abundance froze at a fixed value. This freeze-out abundance depends sensitively on the annihilation cross-section. If the cross-section is too large, WIMPs annihilate too efficiently, and their relic abundance is too low. If the cross-section is too small, too many survive to the present day, overfilling the universe with dark matter. The observed density of dark matter in the universe today, well measured from the cosmic microwave background and large-scale structure surveys, implies a specific range for the WIMP annihilation cross-section. This is sometimes called the thermal relic cross-section, and it comes out to approximately 3 × 10 to the negative 26th cubic centimeters per second in the units particle physicists use. This is a remarkably specific prediction, and it turns out to be exactly the cross-section needed to produce an observable gamma-ray signal in the dark matter halo not so large that WIMPs would have all annihilated away, and not so small that the signal would be undetectable. This coincidence that the WIMP annihilation cross-section derived from cosmological abundance arguments is precisely the cross-section needed to produce an observable indirect detection signal is sometimes called the WIMP miracle. It is one of the strongest theoretical arguments for WIMPs as the dark matter candidate. The fact that a particle motivated entirely by considerations of early universe thermodynamics naturally produces a detectable signal in gamma-ray observations of galactic halos is, to put it plainly, the kind of elegant quantitative agreement that physicists find deeply compelling. If Tatani's signal holds up, the WIMP miracle will have been more than a theoretical curiosity. It will have predicted, correctly and quantitatively, where and at what energy to look for dark matter before the observation was made. That is the gold standard of theoretical physics, a prediction that precedes and is confirmed by experiment. There is another observational test that scientists are hoping to apply to Tatani's signal. The Milky Way's dark matter halo is not perfectly smooth. Like all dark matter halos, it is expected to contain substructure, smaller clumps of dark matter that formed during the hierarchical assembly of the halo over cosmic time. These subhalos would produce localized concentrations of dark matter that could boost the WIMP annihilation rate above what a smooth halo alone would predict. The presence of substructure could help explain why the signal Tatani sees appears brighter than the simplest smooth halo model would naively predict, potentially resolving the tension with expectations about WIMP density. Probing this substructure requires higher resolution observations than are currently available. But next-generation gamma-ray telescopes, including the proposed all-sky medium-energy gamma-ray observatory known as AMEGO, and the Advanced Particle Astrophysics Telescope, are designed with exactly this kind of sensitivity improvement in mind. These instruments, if funded and built in the coming decade, would be able to resolve individual dark matter clumps in the Milky Way's halo for the first time. The Milky Way's dwarf spheroidal satellite galaxies deserve special emphasis as the next observational target for follow-up searches. These objects, small faint galaxies orbiting the Milky Way at distances of tens of thousands to hundreds of thousands of light years, have some of the highest dark matter to stellar mass ratios of any known objects. In some dwarf spheroidals, dark matter may account for more than 90% of the total mass. This extraordinary dark matter dominance makes them ideal laboratories for dark matter searches because the astrophysical backgrounds, pulsars, supernova remnants, actively star-forming regions are minimal. There are few conventional sources of gamma rays in dwarf spheroidals, which means that any gamma ray emission detected from these objects would be much easier to attribute to dark matter annihilation without the complicated background subtraction that challenges galactic center and galactic halo. Searches. If the WIMP annihilation interpretation of Tatani's halo signal is correct, and if the WIMP mass and cross-section implied by the halo signal are plugged into predictions for dwarf spheroidal emission, those objects should be detectable with the current Fermi Telescope, or with relatively modest improvements in sensitivity. Dozens of known Milky Way dwarf spheroidals have already been searched for gamma-ray emission, and the current results are consistent with, but do not yet confirm, the WIMP interpretation. The Vera Rubin Observatory, by conducting a comprehensive survey of the southern sky, is expected to discover many new dwarf spheroidal galaxies that have not yet been identified, extending the sample available for dark matter searches and potentially providing the decisive corroborating evidence. It is also worth considering what it would mean scientifically if Tatani's signal is confirmed as dark matter, but turns out to be inconsistent with the simplest WIMP models. This would not be a failure, it would be a refinement. Science often progresses by ruling out simple hypotheses and converging on more specific ones. If the gamma-ray signal requires, say, a WIMP mass or annihilation channel that differs from naive theoretical predictions, that discrepancy itself would be scientifically valuable. It would constrain the parameter space of supersymmetric models in ways that laboratory experiments cannot yet reach, and it would tell particle theorists which versions of their models to focus on. The dialogue between observation and theory in this field is iterative. Every measurement, positive or null, feeds back into the theoretical framework and sharpens our understanding. The relationship between the theoretical and observational sides of dark matter research is unusually tight compared to many areas of physics. Cosmological simulations of structure formation, enormous numerical calculations that model the gravitational evolution of billions of particles representing dark matter and ordinary matter from the Big Bang to the present, have become sophisticated enough to make detailed predictions about the distribution of dark matter at every scale, from the overall shape of the halo to the density profile near the galactic center to the number and mass function of satellite galaxies. These predictions are testable with current and near-future observations, and the comparison between simulation predictions and observations provides one of the most powerful tools available for constraining dark matter properties. One of the most discussed tensions in this comparison is the so-called core cusp problem. N-body simulations of cold dark matter generically predict that dark matter halos should have a steeply rising density toward their centers, a cusp. But observations of low surface brightness galaxies and dwarf spheroidals sometimes appear to show dark matter distributions with a flat central density, a core. Whether this discrepancy reflects physics that the simulations are missing, such as the gravitational effects of supernovae and gas outflows on the dark matter distribution, or whether it indicates that dark matter itself has properties different from those assumed in cold dark matter models, has been debated for 2 decades without a definitive answer. If WIMPs are confirmed as dark matter, this core cusp tension would need to be resolved within the WIMP framework. Some researchers argue that including realistic baryonic physics, the feedback from star formation, supernovae, and active galactic nuclei on the surrounding matter naturally produces cores from initially cuspy halos without requiring any changes to the dark matter physics. Others argue that self-interacting dark matter, in which dark matter particles interact with each other through a new force beyond gravity, could naturally produce cores while preserving the large-scale successes of cold dark matter. These are questions that the next decade of observations should help resolve. The Vera Rubin Observatory will measure the properties of thousands of dwarf galaxies with unprecedented precision, allowing a comprehensive test of the predicted relationship between halo structure and stellar content. Gravitational lensing surveys will map the dark matter distribution in clusters with a resolution not previously achievable. And continued analysis of Fermi data and observations from new gamma-ray instruments will search for the spatial and spectral signatures that distinguish different dark matter candidates. The universe is staggeringly large, and most of its matter is hidden from us. But the tools we have built, from the particle accelerator tunnels beneath Switzerland to the liquid xenon detectors in gold and silver mines in the American West, to the digital camera atop a mountain in Chile, to the satellite telescope orbiting above the atmosphere that has been patiently collecting gamma rays for 15 years, are beginning to form a picture. Not a complete picture, not yet, but the outlines are becoming visible. Fritz Zwicky looked at the Coma cluster in 1933 and recognized that something invisible was holding it together. He didn't know what it was. He didn't have the tools to find out. He only knew it had to be there. 90 years later, we have built the tools, we have refined the theory, we have collected 15 years of gamma-ray photons arriving from the halo of our own galaxy. And in that data, a signal has appeared in the right place, at the right energy, with the right shape. Whether it is dark matter or not, the search will continue. Because the question is too important, and the universe is too strange to stop asking. Subscribe now, because the next part is something most people miss, and I don't want you to lose it later. The universe held this secret for 13.8 billion years. We may be months or years away from reading it. To place the current moment in its proper historical context, it helps to trace the full arc of how our understanding of the universe's composition has evolved over the past century. Before the 1920s, astronomers broadly assumed that the universe was filled with the matter. They could see stars, gas, dust, organized into galaxies that themselves constituted the major structures of the cosmos. The idea that a substantial fraction of the universe's mass might be invisible was not on the scientific agenda. The tools available didn't raise the question. Edwin Hubble's observations in the late 1920s changed everything at the largest scale. By measuring the redshifts of distant nebulae and establishing that they were galaxies far outside the Milky Way and that they were receding from us at velocities proportional to their distances, Hubble demonstrated that the universe was expanding. This single observation transformed cosmology overnight. If the universe is expanding, it had to have been smaller in the past. If you run the clock backward, all the matter in the observable universe converges on a single point, or at least on a state of enormous density and temperature at a finite time in the past. This was the intellectual foundation of what we now call the Big Bang model. The Big Bang model, developed and refined throughout the 1930s, 40s, and 50s, made specific predictions. It predicted that the early universe should have been hot enough for nuclear reactions to occur, synthesizing light elements, hydrogen, helium, and trace amounts of lithium in proportions that can be calculated precisely. It predicted that the universe should be filled with a thermal background of radiation left over from the hot early phase, now cooled to a few degrees above absolute zero. Both of these predictions were confirmed observationally. Big Bang nuclear synthesis calculations matched the observed abundances of light elements in the universe with extraordinary precision, and the cosmic microwave background was discovered in 1965 by Arno Penzias and Robert Wilson, work for which they received the Nobel Prize in Physics in 1978. Dark matter fits into the Big Bang picture in a specific and constrained way. The cosmic microwave background carries an imprint of the density fluctuations in the early universe. The tiny variations in temperature from one direction to another that correspond to regions of slightly higher and lower density. These fluctuations have been measured with extraordinary precision by a series of satellite experiments, culminating in the Planck satellite's observations in the 2010s. The statistical properties of these temperature fluctuations depend on the amount of ordinary matter, and dark energy in the universe. By fitting the observed fluctuation pattern to theoretical models, cosmologists have determined that the universe is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, with error bars tight enough to make these figures reliable at the percent level. This determination of the dark matter density is completely independent of any galactic rotation, curve, or galaxy cluster velocity dispersion measurement. It comes from the physics of the early universe, encoded in the light that has been traveling to us for 13.8 billion years. The fact that multiple, completely independent methods, rotation curves, velocity dispersions, cluster dynamics, gravitational lensing, and the cosmic microwave background all converge on the same dark matter density is perhaps the strongest possible evidence that dark matter is real and that it has the properties we attribute to it. One of the most beautiful confirmations of dark matter's reality came in 2006 from an observation of the Bullet Cluster, a system consisting of two galaxy clusters that passed through each other. During the collision, the hot gas in each cluster, which makes up the bulk of the ordinary matter in clusters, was slowed by electromagnetic interactions and lagged behind the dark matter, which passed through the collision largely unimpeded because it interacts only gravitationally. By mapping the distribution of mass through gravitational lensing and comparing it to the distribution of the hot X-ray emitting gas, astronomers found that the mass was concentrated in two clumps separated from the gas exactly where the dark matter should have ended up after the collision. The separation between the mass and the gas was so clear and so large that it effectively ruled out attempts to explain galaxy cluster dynamics through modifications of gravity alone without invoking actual dark matter particles. The bullet cluster is one of those rare observations in science that is almost impossible to misinterpret. The data tells a clear and unambiguous story. Dark matter is real. It exists in extended halos around galaxies and clusters. It interacts gravitationally but not electromagnetically, and it passes through itself and through ordinary matter during collisions with at most a small interaction cross-section. Every property the bullet cluster data reveals is consistent with the WIMP picture and inconsistent with the simplest alternatives. Given all this accumulated evidence, the scientific consensus on dark matter's existence is overwhelming and has been for decades. The open question, the one that Tatani's paper directly addresses, is what dark matter is made of. And that question has profound implications beyond astrophysics. If WIMPs are the dark matter, they must be produced somehow in the early universe. The standard picture thermal production during the hot Big Bang, followed by freeze-out, is well understood and makes specific predictions about WIMP properties. But there are alternatives. WIMPs could have been produced non-thermally, through the decay of heavier particles. They could have been produced in the context of extraspatial dimensions, as some theories beyond the standard model propose. They could be connected to the matter-antimatter asymmetry, the still unexplained reason why the early universe produced slightly more matter than antimatter, leaving behind the matter-dominated universe we inhabit today. Each of these production mechanisms leads to different predictions for WIMP properties and different expectations for indirect detection signals. Distinguishing between them observationally would require not just detecting WIMPs, but measuring their properties precisely enough to discriminate between models. This is a long-term research program that stretches well into the coming decades. The dark matter problem also connects to some of the deepest questions about the nature of space and time. In general relativity, gravity is not a force in the conventional sense. It is the curvature of space-time produced by mass and energy. Dark matter, with its gravitational effects, curves space-time. It bends the paths of light and the trajectories of galaxies. It determines the large-scale geometry of the universe. Understanding dark matter is therefore, in part, an exercise in understanding the geometric structure of the cosmos, how mass is distributed, how that distribution evolved from early conditions, and how it will continue to evolve into the future. The future of the universe depends in part on dark matter. In the very long run, on timescales of hundreds of billions to trillions of years, the universe's expansion will continue to accelerate under the influence of dark energy. Stars will burn out. Galaxies will grow dim. Black holes will eventually evaporate through Hawking radiation. Dark matter halos may gradually dissolve as their constituent particles slowly scatter and escape. Whether WIMPs survive to those remote epochs, or whether they have some very slow decay or interaction process that eventually dissipates them, is a question that current theory cannot definitively answer. But it is one that the identification of dark matter's nature would make tractable. These are breathtaking spans of time and distance to contemplate, and the investigation of dark matter spans all of them from the first fractions of a second after the Big Bang, when WIMPs were produced in the hot primordial plasma, to the present day, when they circulate in the halo of the Milky Way, occasionally annihilating and releasing gamma rays that a satellite telescope detects from orbit, to the far future, when their ultimate fate will be governed by physics we are only beginning to understand. The human story of dark matter research is also worth telling. Fritz Zwicky was a difficult man who had the right instinct at the right time and was largely ignored. Vera Rubin faced the additional obstacle of being a woman in a field that was historically resistant to women. She was initially denied access to the Palomar Observatory because women were not permitted to use it, an institutional failure that reflected broader patterns of exclusion in 20th century science. She persisted anyway, made measurements that could not be ignored, and eventually received recognition that, while delayed, became universal. The observatory named for her is a lasting statement about the value of her contribution and an acknowledgement of what institutional bias cost the field during the decades of her career. The researchers working on dark matter today, including Dr. Tatani at the University of Tokyo, are part of a global community that spans every continent and includes every demographic. The questions being asked are so hard and the tools required so sophisticated and expensive that no single institution or country could pursue them alone. The Fermi Telescope is a NASA mission with significant international contributions. The Vera Rubin Observatory is funded by the United States Department of Energy and the National Science Foundation, with a global scientific collaboration that includes researchers from dozens of countries. The Large Hadron Collider at CERN represents the contributions of more than 100 countries. Underground dark matter detectors operate in mines in the United States, Canada, Italy, China, and Australia, each with international science teams. This global scientific enterprise is one of the most impressive collective intellectual efforts in human history. It operates across political boundaries, language barriers, and time zones, unified by a shared commitment to understanding the fundamental nature of the universe. The questions it pursues: what is dark matter? What is dark energy? Why does the universe have the structure it has? Are not practical questions in the short term. They do not have immediate technological applications, but they are the deepest questions that science can ask about the nature of reality, and the answers, when they come, will define what it means to be a scientifically literate civilization. Gamma rays are a good metaphor for the entire enterprise. They travel at the speed of light from their point of origin to the detector that captures them. The gamma rays Tatani analysed were produced in our galaxy's halo at distances ranging from a few thousand to several tens of thousands of light years. They have been travelling through space for that entire time, carrying information about the process that created them, waiting to be intercepted by a detector sensitive enough to record their arrival and smart enough to recognise what they signify. Science is the act of building those detectors and developing that sensitivity. It is the act of learning to read signals that the universe has been sending for billions of years, encoded in light and gravity and the structure of particles, waiting to be deciphered by minds that evolved billions of years after they were sent. Dark matter has been shaping the cosmos since before the first star existed. It has been woven into the fabric of the universe since the first second after the Big Bang. In that sense, it has been all around us for our entire existence, as a species, as a planet, as a solar system, as a galaxy. The fact that we are only now, in the early 21st century, beginning to see its direct signature, is not an indictment of how long it took. It is a remarkable achievement of scientific progress, a testament to what human curiosity, ingenuity, and collaborative effort can accomplish when directed at the hardest questions. Whether Tatani's signal turns out to be the definitive detection or a stepping stone toward it, the trajectory of the field is clear. The tools are better than they have ever been. The theoretical framework is more refined than it has ever been. The global scientific community is larger and more capable than it has ever been. And the observational data, accumulating at terabytes per night from observatories around the world and in orbit, is richer than anything previous generations of scientists could have imagined. The answer is out there. The signal may already be in the data, waiting to be recognized. If Tatani is right, it already has been. 90 years is a long time to wait for an answer. But in cosmic terms, it is barely an eye blink. The universe has been keeping its secrets patiently. We are only beginning to learn how to ask it the right questions in the right language. And that, perhaps, is the most remarkable thing of all. Consider for a moment how completely different our picture of the universe would look without dark matter. In a universe without dark matter, the first stars would have formed much later than they did, because there would have been no early gravitational architecture to concentrate the first clouds of hydrogen. Galaxy formation would have proceeded more slowly, and galaxies themselves would be less massive than they are. The large-scale structure of the universe, the cosmic web of filaments connecting galaxy clusters, with enormous voids between them, would be far less pronounced. Our own Milky Way might not exist in its current form, or might have formed much later, meaning the solar system might not have had time to form and evolve complex life by the age our universe has currently reached. In a very real sense, dark matter is the reason we are here to ask questions about it. The gravitational scaffolding it provided in the early universe created the conditions for stars, planets, and ultimately life to arise. It is the silent architect behind the cosmos we inhabit, and we know nothing fundamental about what it is. That is the essential paradox at the heart of modern cosmology. We can calculate the density of dark matter in the universe to within a few percent. We can map its distribution across billions of light years using gravitational lensing. We can trace its influence on galaxy formation back to within a few 100 million years of the Big Bang. We can predict how its clumping seeded the first structures in the universe. All of this we can do without knowing what dark matter actually is. It is as if you could calculate the trajectory, mass, and density of every brick in a building, but still had no idea whether the bricks were made of clay, concrete, stone, or some material that had never been identified. You would know an enormous amount about the building, but the fundamental question of what it was made of would remain entirely open. This analogy captures something real about the state of dark matter science. Our gravitational and cosmological tools are extraordinarily powerful for characterizing dark matter's macroscopic behavior. But identifying the microscopic identity of dark matter, the actual particle physics of what it is, requires a completely different class of tools. It requires particle detectors capable of sensing the energy released when a dark matter particle scatters off a nucleus. It requires particle accelerators capable of creating dark matter in high-energy collisions. And it requires gamma-ray telescopes capable of detecting the photons produced when dark matter annihilates in the halos of galaxies. All three approaches are being pursued simultaneously, and they are more complementary than competitive. A direct detection event in an underground laboratory would tell you the WIMP's mass and scattering cross-section, but would give you limited information about its annihilation properties. An accelerator signal would tell you the WIMP's mass and production channels, but would give you limited cosmological context. An indirect detection signal from gamma-ray astronomy tells you the WIMP mass and annihilation rate in galactic halos, but gives you limited information about laboratory-accessible properties. Only by combining results from all three approaches can physicists fully characterize a dark matter particle and confirm beyond doubt that it matches the cosmological dark matter. This multifaceted confirmation is the scientific standard that the community has set for a genuinely definitive discovery, and it is a high standard deliberately set to avoid premature claims. The WIMP miracle mentioned earlier has a specific quantitative meaning that is worth unpacking more carefully, because it illustrates why WIMPs became the dominant dark matter hypothesis in the first place. In the early universe, at temperatures above roughly 10 giga-electron volts, which corresponds to the earliest fractions of a second after the Big Bang, WIMPs would have been produced and destroyed at the same rate, maintaining a thermal equilibrium with the other particle species in the hot plasma. As the universe expanded and cooled below this temperature, WIMP production slowed because the average collision energy was no longer sufficient to create new WIMPs. The only process that continued was WIMP annihilation pairs of WIMPs destroying each other. As the density of WIMPs dropped with the expansion of the universe, even annihilation became increasingly rare, until at some point the universe became so sparse that WIMPs could no longer find each other frequently enough to annihilate. At this freeze-out point, the co-moving density of WIMPs became fixed. They stopped disappearing, and their abundance was locked in. The calculation of this freeze-out abundance requires only two inputs: the mass of the WIMP and its annihilation cross-section. Remarkably, for a particle with a mass between roughly 10 and a few thousand giga-electron volts and an annihilation cross-section of the order predicted by weak force interactions, the resulting freeze-out abundance exactly matches the observed dark matter density. This is the WIMP miracle, the fact that a particle motivated by purely particle physics considerations, with no reference to cosmology, naturally produces the right amount of dark matter through thermal freeze-out. It would be an extraordinary coincidence if WIMPs were not the dark matter. The thermal relic cross-section implied by this calculation is approximately 3 × 10 to the negative 26th cubic centimeters per second. This number is important because it directly determines how bright the expected gamma-ray signal from WIMP annihilation in galactic halos should be. If this cross-section is correct, and if the dark matter halo has the density profile predicted by N-body simulations, the gamma-ray flux at Earth from the Milky Way's halo is calculable. It is faint, but not impossibly faint. It is within the detection capability of the Fermi Telescope over 15 years of observation. This is precisely the setup for Totoni's analysis. He was looking for a signal that theory had predicted should be there at roughly this brightness, with roughly this spectral shape, spread across roughly this region of the sky. And he found something that matches those predictions to a degree that is scientifically striking. One of the more subtle aspects of the analysis involves the so-called J factor, a quantity that encodes the integral of the dark matter density squared along the line of sight and across the angular region being analyzed. Because WIMP annihilation requires two WIMPs to meet, the annihilation rate at any point goes as the square of the local density. The J factor therefore weights the signal toward the regions of highest dark matter density, and it depends sensitively on the assumed dark matter density profile. Different profile models, the Navarro-Frenk-White profile, the INASTO profile, the isothermal profile, give somewhat different J factors for the same region of sky, introducing a theoretical uncertainty in the predicted signal brightness. Totoni's analysis accounts for these uncertainties and finds that his observed signal is consistent with the WIMP model across the range of commonly used density profiles. This robustness to the assumed density profile strengthens the case that the signal is not an artifact of a particular modeling choice. The spectral analysis is equally important. Different WIMP annihilation channels produce different gamma-ray spectra. Annihilation through bottom quark pairs produces a characteristic continuum spectrum with a specific shape peaking at roughly 1/10 of the WIMP mass in giga-electron volts. Annihilation through W boson pairs, or top quark pairs, produces slightly different spectral shapes. By fitting the observed spectrum to predictions from different annihilation channels and different WIMP masses, Totoni and collaborators can constrain which models are consistent with the data. The peak at 20 giga-electron volts is consistent with WIMP masses in the range of roughly 40 to 100 giga-electron volts. Annihilating primarily through bottom quark pairs a theoretically natural and commonly predicted scenario. The fact that a specific annihilation channel and a specific mass range can be identified from the spectrum, rather than the data being consistent with an arbitrarily wide range of parameters, is an important feature of the result. Dark matter signals are not expected to fit every theoretical scenario equally well. The specificity of the spectral fit is part of what gives the result its credibility. There is also a consideration involving systematic uncertainties in the Fermi background model. The Fermi collaboration has developed sophisticated models of the diffuse gamma-ray background, the emission from cosmic ray interactions with interstellar gas and radiation fields throughout the galaxy. These models are the product of decades of work and are continuously updated as new sources are identified and new data is incorporated. Any residual signal in Totani's analysis depends on these background models being accurate. If the background model underestimates the conventional emission in the halo region, the apparent dark matter signal could be partly or wholly attributable to conventional physics that wasn't correctly subtracted. Totani's paper addresses these systematic uncertainties carefully, exploring how the signal changes under different background model assumptions, and finding that it is present across the range of plausible background models. This robustness to background assumptions is an important cross-check, but the community recognizes that systematic uncertainties in diffuse emission modeling are among the hardest to fully characterize, and independent verification using different analysis methods and potentially different gamma-ray datasets will be an important part of validating the result. The International Gamma-Ray Astrophysics Laboratory, known as INTEGRAL, has been observing the sky in gamma rays and X-rays since 2002. While its energy range is different from Fermi's focusing on lower energy gamma rays, integral data may provide complementary information about the spectral shape of any dark matter signal in the lower energy range. Similarly, future instruments like the Compton Spectrometer and Imager, or COSI, scheduled for launch in the coming years, will cover an important energy window between X-ray and gamma-ray observations that current instruments don't fully address. Each new instrument adds a piece to the picture. The picture we are assembling is of the dark matter halo of the Milky Way, its spatial distribution, its spectral characteristics, its density profile. If dark matter is producing a signal, that signal should be coherent across all energy ranges and all observation angles. As the catalogue of observations grows, the consistency or inconsistency of a dark matter interpretation across multiple instruments will be a powerful test. There is one more conceptual point worth making about what it means to detect dark matter. When physicists talk about detecting a new particle, they are usually thinking about measuring its properties, its mass, its charge, its spin, its interactions with other particles. For ordinary particles, this is straightforward in principle, even if technically demanding. A proton, for example, can be slowed down, captured, studied at leisure. Its properties are measured to many decimal places. Dark matter is fundamentally different. We cannot capture it. We cannot contain it. We can only infer its properties from the traces it leaves, the light it bends, the gas it drags, the gamma rays it produces when it occasionally annihilates. In this sense, dark matter is more like a geological phenomenon, an earthquake, or a continental drift than like a laboratory specimen. We understand it through its effects on things we can observe, not through direct study of the thing itself. This indirect approach to understanding nature is not new. It is how we first understood the structure of atoms, through the patterns of light they emit. It is how we first understood the existence of black holes, through the behavior of matter and light near them. It is how we first understood the expansion of the universe, through the redshift of distant galaxies. Nature does not always present itself for direct examination. Sometimes it reveals itself only through imprints left in other things, and science must learn to read those imprints. Totani's gamma-ray signal is an imprint. Whether it is dark matter's fingerprint or something else's will be determined by the patient accumulation of more data, more independent analyses, and more theoretical refinement. But the signal is there, in 15 years of accumulated photons, each one having travelled across tens of thousands of light years to arrive at the Fermi Telescope's detector, and it is pointing in a very specific direction. That direction is toward the dark matter halo of the Milky Way. That direction is toward a population of particles that have been present in this galaxy since its formation, orbiting in an enormous invisible sphere, occasionally meeting each other with enough energy to annihilate and release a flash of gamma radiation. That direction, if the physics is right, is toward a 90-year-old mystery finally beginning to resolve. The cosmos is not obligated to make its deepest secrets easy to find. Dark matter has been extraordinarily stubborn, invisible to every instrument we pointed at it, leaving only gravitational traces that we could interpret but not confirm as evidence of a specific particle. The fact that we have kept looking, refining our instruments, developing new techniques, and building new theoretical frameworks over 9 decades is a testament to the human drive to understand. We are closer than we have ever been. The signal in the Fermi data may be the first clear glimpse of what dark matter actually is. Or it may lead to something even more surprising, a new kind of physics that nobody has fully imagined yet. Either way, what comes next will be extraordinary. Follow the story. The universe is speaking, and scientists are finally learning to listen. Let's think carefully about what it would mean for human civilization if dark matter were identified conclusively. The immediate consequence would be scientific. The standard model would require an extension, supersymmetry, or some alternative framework would gain decisive empirical support, and decades of theoretical work would either be confirmed or redirected. But the longer-term consequences would be more far-reaching. Every previous revolution in our understanding of fundamental physics has eventually led to technology that transformed civilization. The understanding of electromagnetism in the 19th century, developed through seemingly abstract experiments with wires and magnets and batteries, led within a few generations to radio, television, computers, and the entire digital infrastructure of modern life. The understanding of quantum mechanics in the 20th century, developed through equally abstract debates about the nature of light and electrons, led to the transistor, the laser, the MRI scanner, and the fiber optic networks that carry global communications. Nuclear physics, originally motivated by purely scientific curiosity about radioactivity, led to both nuclear power and nuclear medicine. Dark matter, if identified as a specific particle, would open similar doors, though it is impossible to predict exactly which ones. A new particle with specific interaction properties, beyond what the standard model describes, represents a new handle on the physical world. The history of technology suggests that new physical knowledge, even when it appears purely academic, has a way of finding practical applications that nobody anticipated at the time of discovery. The ability to produce, control, or detect dark matter particles, however distant that prospect seems today, could potentially have implications we are not currently in a position to imagine. There is a more immediate practical benefit as well. The techniques developed to search for dark matter ultra-sensitive particle detectors, sophisticated signal processing algorithms capable of finding tiny signals in enormous noisy datasets, gravitational lensing analysis tools, gamma-ray spectral analysis methods have direct applications in medical physics, security technology, materials science, and data science. The engineering challenges of building a multi-ton liquid xenon detector with the purity required for dark matter detection have advanced cryogenic technology and materials science in ways that benefit other fields. The computational challenges of processing petabytes of telescope data have driven the development of new machine learning approaches that are being applied across science and industry. Big science is never purely academic. The pursuit of fundamental understanding generates capabilities and techniques that percolate through the broader technological ecosystem in ways that are difficult to predict and easy to underestimate. Dark matter research has been pursued at this level of intensity and global coordination for several decades. The Milky Way itself is embedded in a dark matter halo that extends several 100,000 light-years from the galactic center, far beyond the visible disk of stars and gas. This halo is not smooth. It contains hundreds of smaller subhalos that are the remnants of smaller galaxies that were absorbed by the Milky Way over its history through the hierarchical process of structure formation that characterizes cold dark matter. Cosmology. Some of these subhalos are massive enough to host visible dwarf galaxies that we can observe. Others are too small to have captured enough gas to form stars, and are entirely dark, predicted by cold dark matter models, but invisible to telescopes, except through gravitational lensing. The number and distribution of these dark subhalos is a specific prediction of the cold dark matter model. If WIMPs are the dark matter, and if the cold dark matter model is correct, there should be a specific population of dark subhalos with specific properties. Gravitational lensing observations and the dynamical behavior of streams of stars in the Milky Way's halo provide ways to search for these subhalos. So far, the evidence is broadly consistent with cold dark matter predictions. Though there remain some tensions, there appear to be fewer bright satellite galaxies around the Milky Way than the simplest cold dark matter models predict, a problem known as the missing satellites problem. This tension, like the core cusp problem, may be resolved by better modelling of baryonic physics effects on halo evolution, or it may eventually point to modifications in the dark matter model itself. Resolving these tensions requires observations at the frontier of sensitivity, exactly what the Vera Rubin Observatory is designed to provide. By surveying the southern sky to unprecedented depth over 10 years, Rubin will discover a comprehensive census of faint dwarf galaxies around the Milky Way. If the missing satellites problem is explained by baryonic physics effects on visible galaxy formation, the faint galaxy population discovered by Rubin should match predictions once those effects are properly modelled. If it is not explained by baryonic effects, the discrepancy will become sharper and more difficult to dismiss. Similarly, stellar stream observations, which use the gravitational disruption of streams of stars torn from globular clusters as a probe of the dark matter subhalo population, are becoming increasingly precise. The Gaia Space Observatory, launched in 2013 and still operating, has provided exquisitely precise positions and velocities for more than 1 billion individual stars in the Milky Way. Using this data, astronomers have traced the structure of stellar streams in the galactic halo with unprecedented detail. Gaps, distortions, and irregular structures in these streams can reveal the presence of dark subhalos passing through and gravitationally perturbing them. Early analyses of Gaia data have found candidate perturbations consistent with dark subhalo encounters, though definitive confirmation requires additional observations and modelling. All of this observational work feeds into a comprehensive program aimed at understanding dark matter from multiple angles simultaneously. The picture that is emerging, still incomplete, still ambiguous in key details, but progressively clearer, is of a universe in which dark matter is real, is present in halos around all galaxies, has the density profile predicted by cold dark matter models to a rough approximation, and may be annihilating in those halos at a rate consistent with WIMP physics. The keyword is may. Science requires more than consistency. It requires confirmation through independent methods and the elimination of alternative explanations. That process is underway, driven by a global community of researchers using the most sophisticated instruments ever built. There is something deeply human about the dark matter search that goes beyond its scientific importance. It represents a confrontation with the limits of our perception. We evolved to sense the world through light. Our eyes are specialized for visible wavelengths of the electromagnetic spectrum, and even our instruments are largely designed to detect light of one kind or another. Dark matter is a category of reality that is fundamentally beyond this mode of perception. It exists. It dominates the mass of the universe. It has shaped the cosmos from its earliest moments, and it passes through us constantly without interacting, without leaving any signal that our evolved senses or our light-based instruments can normally detect. Detecting it requires building instruments specifically designed to sense the tiny secondary effects of its rare interactions, or to detect the gamma rays that its annihilation produces, or to map the distortions in light paths that its gravity creates. These are indirect methods reconstructing the presence of something invisible from the signals it leaves on things that are visible. In this sense, the dark matter search is a metaphor for the scientific enterprise itself. Science is fundamentally the project of extending human perception beyond its evolved limits of learning, to see things that are not directly visible, to hear things that are not directly audible, to measure things that no unaided sense could register. Every instrument humans have built for scientific purposes is an extension of this project, and the dark matter search represents one of its most ambitious expressions, directed at a component of reality that is specifically and fundamentally invisible to every conventional mode of detection. The fact that we have narrowed the search to specific particle candidates, specific mass ranges, specific energy signatures, and specific spatial distributions within our galaxy, that we have arrived at a point where a specific signal in specific data might be the first direct evidence of this invisible substance, is a remarkable achievement of the problem. Scientific project. And now we wait. We wait for more data from the Fermi Telescope. We wait for the first dark matter science results from the Vera Rubin Observatory in 2026. We wait for the underground direct detection experiments to extend their sensitivity into mass ranges that have not yet been probed. We wait for the particle physicists to refine their constraints on supersymmetric parameter space. We wait to see whether the 20 giga-electron-volt signal in the galactic halo gamma-ray background holds up under further scrutiny, or whether some conventional astrophysics explanation emerges that accounts for it. The universe has been patient with us. It has held its secrets for 13.8 billion years. We have been asking the right questions for barely a century. 90 years from Zwicky's first observation. 50 years from Vera Rubin's rotation curve measurements. 15 years of Fermi gamma-ray data, and now, possibly, a signal. The answer may be months away. It may be years, but the trajectory is clear. The tools are ready. The data is accumulating. The theoretical framework is in place. And somewhere in the halo of our galaxy, dark matter is doing what it has always done, circulating silently in the dark, making our existence possible, waiting to be understood. We are almost there. The search for dark matter's identity is not happening in isolation. It unfolds alongside other major open questions in fundamental physics, and the answers to those questions may be intertwined in ways that aren't yet obvious. One of the most pressing open questions is the nature of dark energy, the mysterious component of the universe that is causing its expansion to accelerate. Dark energy accounts for roughly 68% of the total energy content of the universe, compared to dark matter's roughly 27% and ordinary matter's roughly 5%. We understand dark matter better than we understand dark energy. At least we have a specific particle physics candidate to test. Dark energy doesn't even have a compelling particle physics analog. It may be a property of space itself, a fixed energy density associated with empty spacetime called the cosmological constant, first introduced by Einstein and famously retracted before later observations forced its reintroduction. Or it may be a dynamic field that evolves over time, called quintessence. The Vera Rubin Observatory will investigate both dark matter and dark energy simultaneously. Its weak lensing surveys statistical maps of how galaxy shapes are distorted by the gravitational influence of matter along the line of sight, will probe both the distribution of dark matter and the growth rate of cosmic structure, which depends on the balance between dark matter's gravitational pull and dark energy's accelerating expansion. Understanding the balance between these two invisible components is one of the central goals of 21st century cosmology. It is striking that we live in a universe whose content is dominated by substances we don't understand. Ordinary matter, the stuff of atoms, chemistry, biology, stars, and planets, is a minor component. If dark matter and dark energy together constitute 95% of the universe's total energy content, then everything we can see, touch, and interact with directly is a tiny fraction of what exists. Our entire observable and tangible world is, in a cosmic accounting sense, the foam on the surface of an ocean whose depth and composition remain largely unknown. This is not a reason for despair, it is an invitation. The universe is stranger and richer than any pre-scientific civilization imagined. Every discovery of a new component of reality, whether it was the germ theory of disease, the atomic structure of matter, the quantum nature of energy, or the expanding cosmos, has expanded our understanding without diminishing the wonder. Learning what dark matter is will not make the universe less mysterious. It will make it more complex and more fascinating in new ways we can't fully anticipate. Physics has a long history of solving one mystery, only to reveal several more behind it. The discovery of the electron led to quantum mechanics. Quantum mechanics led to the need for quantum field theory. Quantum field theory led to the Standard Model. The Standard Model, despite its extraordinary success, leaves too many questions unanswered to be the final word. It doesn't include gravity. It doesn't explain dark matter or dark energy. It doesn't explain the matter-antimatter asymmetry. And it has too many free parameters that have to be measured rather than derived from first principles. Whatever comes next will be built on the foundation of what we know now, and identifying dark matter will be part of that foundation, perhaps a central part. A theory that encompasses ordinary matter, dark matter, gravity, and the quantum world would represent the deepest understanding of physical reality that humans have ever achieved. That theory doesn't exist yet, but the observations being gathered right now, including the signal in Totoni's analysis of Fermi data, are part of the evidence that will eventually constrain it. It is worth thinking about the generations of scientists who will carry this work forward. The researchers who will confirm or refute Totoni's signal, who will analyze the first Vera Rubin Observatory dark matter data releases, who will run the underground detectors of the next decade. Many of them are in graduate school now, or just beginning their postdoctoral careers. Some of them may not have been born yet when the Fermi Telescope was launched in 2008. They will inherit a field that is on the cusp of its most significant discovery. They will have access to datasets and computational tools that would have seemed impossibly powerful to the researchers of a decade ago. And they will ask questions that the current generation hasn't yet thought to formulate. Science is a generational project. The questions Zwicky raised in 1933 were passed on to Vera Rubin, who passed them on to the cosmologists and particle physicists of the 80s and 90s, who passed them on to the current generation working with Fermi data and building the Vera Rubin Observatory. The thread of inquiry runs unbroken across generations, each one adding to the evidence and refining the tools. Somewhere in that chain of inquiry, probably within the next decade or two, comes the discovery that finally answers the question. We don't know which instrument will provide the decisive evidence. We don't know which analysis will be the one that shifts the field from suspicion to certainty. We don't know whether the answer will be WIMPs or axions or something entirely unexpected. What we do know is that the question is the right one. We do know that dark matter is real. We do know that it shapes everything we see in the night sky, and that it shaped the conditions that allowed us to exist and ask these questions. And we know that the human curiosity that drove Zwicky to stare at the Coma cluster through the Mount Wilson telescope in 1933 is the same curiosity that drives researchers today to sift through petabytes of gamma-ray data in search of a signal that should, by every theoretical indication, be there. That continuity of curiosity is the most remarkable thing of all. Not the technology, impressive as it is. Not the scale of the observatories, staggering as they are. Not even the elegance of the theoretical framework that connects particle physics to cosmology across 14 orders of magnitude in scale. The most remarkable thing is that we keep asking, we keep looking, we keep building better instruments and better theories and better analysis tools because we genuinely want to know what the universe is made of. That is what science is. That is what it has always been. And right now, at this precise moment in history, it is closing in on one of its greatest answers. Stay curious, stay engaged. The story is still unfolding. One dimension of this story that deserves more attention is the role of computational physics in the dark matter search. Modern astrophysics cannot proceed without simulation, and the dark matter problem has been one of the primary drivers of computational cosmology since its inception. The first N-body simulations of dark matter halo formation were run in the 1980s on computers that, by today's standards, were barely capable of tracking a few thousand particles through their gravitational evolution. Today, the largest simulations track billions of particles simultaneously, following the formation of cosmic structure from the primordial density fluctuations of the Big Bang to the elaborate web of filaments, sheets, and voids we observe in the present universe. These simulations are not merely illustrative tools, they are quantitative, predictive instruments. When cosmologists run a simulation with a specific dark matter model and specific initial conditions derived from cosmic microwave background measurements, the resulting galaxy population should match what we observe in the real universe. The degree to which it does or doesn't match is a direct test of the dark matter model. The cold dark matter model, with WIMPs as the dark matter particle, has been extraordinarily successful in reproducing the large-scale structure of the observed universe, the distribution of galaxy clusters, the statistics of galaxy sizes and luminosities, the overall shape of the cosmic web. This success on large scales is one of the strongest arguments for cold dark matter, and by extension for WIMPs. The tensions that remain the core cusp problem, the missing satellites problem, the too big to fail problem, are all on small scales, where the details of how ordinary matter interacts with dark matter halos are most important. These small-scale tensions have driven a major effort to incorporate more realistic baryonic physics into simulations modeling star formation, supernova feedback, black hole growth, and its effects on surrounding gas, and the photoionization of gas by early ultraviolet radiation fields. Simulations that include this physics are called hydrodynamic simulations, and they require orders of magnitude more computational resources than pure N-body dark matter simulations. Projects like the Illustris TNG simulation, the Eagle simulation, and the Fire simulation have invested enormous computational effort in modeling these baryonic processes with increasing realism. The preliminary results from these simulations suggest that the small-scale tensions between cold dark matter predictions and observations may be largely resolved once baryonic effects are properly accounted for. The gravitational explosions of supernovae, which rapidly expel gas from the centers of dwarf galaxies, can transform cuspy dark matter profiles into cores. The photoionization of gas by early stars can prevent gas from falling into the smallest dark matter halos, explaining why many predicted small halos appear to be completely dark. If these baryonic solutions to the small-scale tensions are confirmed by upcoming observations, the cold dark matter model will be even more firmly established, and the case for WIMPs as the dark matter particle will be correspondingly stronger. If the tensions persist or worsen when the Vera-Rubin Observatory provides better measurements of the dwarf galaxy population, more exotic dark matter models will receive greater attention. There is also a specific prediction of WIMP physics that connects to the cosmological simulation program. If WIMPs annihilate in galactic halos, they inject energy into the surrounding medium. In the early universe, WIMP annihilation during and after the epoch of recombination, when the universe first became transparent to light, would have heated and ionized the surrounding gas, leaving a detectable imprint on the cosmic microwave background. Specifically, WIMP annihilation in the early universe would broaden the last scattering surface and alter the temperature and polarization fluctuation statistics of the cosmic microwave background in ways that current and future experiments can constrain. Planck satellite observations have already placed limits on how much WIMP annihilation could have occurred in the early universe, and these limits are consistent with but beginning to constrain the parameter space relevant for Titani's signal. Future cosmic microwave background experiments, particularly CMB S4, a proposed ground-based array of telescopes in Chile and at the South Pole, will extend these constraints significantly, providing an independent test of the WIMP interpretation from early universe physics, completely separate from galactic gamma-ray observations. The convergence of early universe constraints from the cosmic microwave background, galactic-scale constraints from gamma-ray observations like Titani's, and local constraints from underground direct detection experiments is precisely the multi-messenger approach that the dark matter community has been working toward for decades. Each probe has different systematic uncertainties and different physical sensitivity. A consistent picture emerging from all three would be extraordinarily powerful. There is one more experimental approach worth discussing that has generated significant excitement in recent years: indirect detection through neutrinos. WIMP annihilation can produce not just gamma rays, but also high-energy neutrinos, depending on the annihilation channel. Neutrinos interact even more weakly than gamma rays. They can pass through the entire Earth without being absorbed, but large underground neutrino detectors like IceCube, buried in the Antarctic ice sheet, are sensitive to the rare interactions that neutrinos do have. WIMPs captured in the gravitational well of the Sun would accumulate in the solar core and eventually annihilate, producing high-energy neutrinos that would emerge from the Sun and potentially be detectable by IceCube. IceCube has searched for this signal and has placed limits that constrain certain WIMP models. The limits are not yet sensitive enough to probe the parameter space most relevant for Titani's gamma-ray signal, but improvements to IceCube and its planned successor, IceCube Gen 2, will extend this reach. A simultaneous neutrino and gamma-ray detection consistent with the same WIMP mass and annihilation channel would be among the most compelling dark matter evidence imaginable. The connection between gamma-ray and neutrino signals is direct and specific. For WIMP annihilation through bottom quark pairs, the ratio of gamma-ray to neutrino production is calculable from the standard model physics of quark decays. If Titani's gamma-ray signal is confirmed, and a corresponding neutrino signal is eventually detected at the predicted rate, the combined detection would constitute the most complete observational characterization of a dark matter particle yet achieved. We are building toward this, not in years, but perhaps in a decade or two. The instruments are being planned and funded. The techniques are being developed. The sensitivity is increasing with each generation of experiments. The universe has been sending these signals for billions of years. The WIMPs in our galaxy's halo have been annihilating and releasing gamma rays and neutrinos since before the Earth was formed. Those particles have been propagating through space, some of them arriving at Earth, passing through it, disappearing undetected, until we built instruments sensitive enough to stop some of them and measure their properties. We stopped some of those gamma rays with the Fermi Telescope. Titani looked at what was stopped over 15 years of observation and found a pattern. That pattern looks like what WIMP annihilation should look like. The research community is now working to determine whether the resemblance is coincidental or causal, whether nature is telling us something fundamental about itself through this signal. That work will continue regardless of whether Titani's specific result survives scrutiny in its current form. The tools, the techniques, and the theoretical framework have been refined to a point where the dark matter problem is genuinely tractable. The answer is within reach, not guaranteed, not imminent with certainty, but achievable within the span of a research career. Fritz Zwicky could not have imagined, staring at the Coma cluster through the Mount Wilson telescope in 1933, that 90 years later, a satellite telescope would be detecting gamma rays from the halo of our own galaxy at an energy consistent with the annihilation of the very particles whose existence he inadvertently inferred. He could not have imagined the theoretical framework that would connect his observation of anomalous galaxy velocities to the quantum field theory of weakly interacting supersymmetric particles. He could not have imagined the computational infrastructure that would simulate billions of dark matter particles through 14 billion years of gravitational evolution in order to predict the shape of the halo whose gamma-ray emission would be compared to satellite observations. But all of that is the direct intellectual descendant of what Zwicky noticed and refused to ignore in 1933. The thread of inquiry runs unbroken from that moment to this one, and it may be approaching its conclusion. The answer, when it comes, will not make the universe less wonderful. It will add another layer of understanding to an enterprise that has been revealing the strangeness and richness of reality for centuries. And it will open new questions about the properties of dark matter particles, about their role in the early universe, about their connection to the deeper theories of physics that lie beyond the standard model. That is how science works. Every answer is also a doorway. Every discovery creates the possibility of the next one. The universe is larger and stranger than any framework we build to describe it. But we keep building better frameworks, and the universe keeps revealing more of itself. Dark matter is out there. It has always been out there, and we are very close to finally knowing what it is. Let us consider the specific observational program that will unfold over the next 5 to 10 years, because it represents one of the most coordinated and multifaceted scientific efforts in history. The timeline is not entirely predictable. Science does not always proceed on schedule, but the instruments are real, the data pipelines are being built, and the scientific community has a clear roadmap. In 2026, the Vera Rubin Observatory is expected to release its first datasets from the beginning of its 10-year legacy survey of space and time. This survey will image the entire accessible southern sky every few nights, building up a time domain catalogue of unprecedented depth and completeness. For dark matter science, the most immediate products will be maps of gravitational weak lensing across the southern sky, statistical analyses of the slight distortions in galaxy shapes caused by the gravitational influence of mass along the line of sight. These maps will reveal the distribution of both visible and dark matter on scales from galaxy halos to cosmic filaments, providing the most comprehensive picture of dark matter's large-scale structure ever assembled. At the same time, Rubin will begin discovering new dwarf spheroidal galaxies around the Milky Way and in the nearby universe. The Milky Way is predicted to have hundreds of satellite galaxies too faint to have been found by previous surveys. Rubin's unprecedented depth will reveal many of them for the first time. Each newly discovered dwarf spheroidal becomes a potential target for dark matter searches, either through gamma-ray observations with Fermi or its successors, or through spectroscopic follow-up to measure the velocities of individual stars and thereby determine the dark matter density profile. Underground direct detection experiments are meanwhile working toward their planned upgrades and next-generation facilities. The Lux Zeppelin experiment in South Dakota is operating with a liquid xenon target of approximately 10 tons, achieving sensitivity to WIMP nucleon scattering cross-sections orders of magnitude below what was accessible a decade ago. The planned XLZD consortium, a collaboration involving the major xenon detector experiments, aims to build a next-generation detector with a target of 40 to 60 tons of liquid xenon, scheduled for the early 2030s. This detector would reach the so-called neutrino fog, the irreducible background of atmospheric and solar neutrinos that scatter off xenon nuclei in a way that mimics WIMP signals, representing the ultimate limit of this detection technique for certain WIMP mass ranges. If WIMP nucleon scattering occurs at rates above the neutrino fog, the next generation xenon detectors will either detect it or rule it out definitively in the accessible mass range. This will be a decisive test. If WIMPs are responsible for Totani's gamma-ray signal with the properties implied by that signal, they should produce a detectable scattering rate in a multi-ton xenon detector. Assuming standard assumptions about the galactic dark matter density in the solar neighborhood, the two probes, gamma-ray emission from halo annihilation and nuclear scattering in underground detectors, are not independent. They test overlapping aspects of WIMP physics, and a consistent detection in both would be overwhelmingly convincing. The Large Hadron Collider's high luminosity upgrade, known as the High Luminosity LHC, or HL-LHC, is scheduled to begin collecting data in the late 2020s. By colliding protons at the same energy but at much higher collision rates than the current LHC, the HL-LHC will probe for supersymmetric particles with even greater sensitivity. If the supersymmetric partners relevant for WIMP dark matter exist and are not too much heavier than the current energy reach, the HL-LHC may produce them directly, allowing their properties to be measured in the controlled environment of a collider experiment. A collider detection of a supersymmetric WIMP with properties consistent with Totani's gamma-ray signal and with an underground detector signal would constitute the most complete and definitive dark matter discovery possible. This convergence of evidence galactic gamma rays, underground nuclear recoils, and particle collider detection is the dream of the dark matter physics community. It is what a convincing identification of dark matter's nature would look like. Whether this convergence occurs in 5 years, 10 years, or longer, it is the logical endpoint of the research program currently underway. The scientific community has learned patience from the dark matter search. For decades, the discovery seemed always to be just around the corner. The next generation of detectors, the next few years of LHC data, the next Fermi analysis would surely bring the answer. And decade after decade, the answer has remained elusive. This has not weakened the case for dark matter. The gravitational evidence has only grown stronger, but it has tempered the optimism about quick discovery and reinforced the importance of the multi-pronged approach. The lesson of this prolonged search is that understanding nature at the deepest level requires patience, persistence, and willingness to follow evidence wherever it leads, even when it leads away from the initially favored hypothesis. If WIMPs are ultimately ruled out as dark matter candidates, the field will not collapse, it will redirect. The constraints placed on WIMPs will themselves be valuable scientific knowledge. They will tell us definitively what dark matter is not, narrowing the universe of possibilities. The techniques developed for WIMP searches will be applied to other candidates. The instruments built for this search will be repurposed for other science, even as they continue the dark matter hunt. Science is not a linear progression toward a predetermined answer. It is an iterative exploration of what nature is actually like, constrained by evidence and refined by experiment. The path may not be straight, but the direction toward greater understanding, greater precision, greater insight into the fundamental nature of the universe is clear. And right now, at this particular moment, that path runs through the galactic halo of the Milky Way at an energy of 20 giga-electron-volts, in a signal that Dr. Tomonori Totani found while sifting through 15 years of gamma-ray observations from a satellite telescope in low Earth orbit. Whether that signal leads to the answer or to the next chapter of the question, it is where the story is most alive right now. It is where the evidence is newest and the scientific excitement is most acute. And it is a signal that connects, through 90 years of scientific inquiry, to the moment a Swiss astronomer in California looked at a galaxy cluster and realized that the universe was hiding something enormous from us. We have been looking for that hidden thing ever since, and we may, at last, be close to finding it. The cosmos does not give up its secrets easily. But it does give them up eventually to those who look carefully enough, with instruments sensitive enough, guided by theories precise enough to tell them where to look and what to expect. We have arrived at that point. The instruments are ready, the theories are refined, the data is accumulating. The universe has kept this secret for 13.8 billion years. The next few years may finally see it revealed. If this helped you even a little, hit subscribe. I'm posting more videos like this, and trust me, you don't want to miss what's coming next. Thanks for watching till the end. I'll see you in the next one.